All right, as you noticed so far, we went through the Oracle network area, each component, both on the database side and the client side, okay, how they are related and used. We talked about the session management, the server process, the type of sessions that could get connected, and the memories that are used there. We talked about our database server, where we have the two components, the instance and the database. And we used SQL, both select and the DMLs, into driving some of the components in this architecture so we know how things look like and why are these different things are being used. However, as you can see, there's still some spaces here that we got to fill up. We're not completely done with this. The other components that I'm going to go through, each one is designed for the certain operations, okay? And depending on you using them or not, they could be used or not be used within your environment, okay? And the build of them depended on the generation where the functionality was introduced. So first, let's complete the rest of our SGA, and then we go to the background processes to complete the instance. So in the SGA, as we said, we have our shared pool. And as we noticed, we have talked about the components that we use in there to manage SQL. There are two more components located in the shared pool. One component here is called the global context area. Now, if you remember, we talked about the context being a namespace in memory, a placeholder for a bunch of variables. We said that in the session, we use a local context that is private to the session that identifies what this session is specifically doing and who the session is for the client application. The global context we use for managing the user itself. Normally, we use the global context for what we call virtual private database, VPD. VPD is our row-level security, as we will cover that in the security class. And when I use that row-level security, we generate where clauses. So when Ron goes here and select asterisk from table employees, database will say, I'm going to go find out what Ron's position is. So it can go search the database, find out Ron is just an instructor. Then it's going to say, well, Ron is an instructor, therefore he can only see his own records. So it could attach a where clause where employee ID equal to Ron's. If, for example, my manager go there, after it finds out there's a manager, it could put a where clause where the department ID equal to the department that that manager is managing. The user may have multiple sessions. That's why we want to put the where clauses in the shared memory, that in case the user has multiple sessions, we don't have to go through the process of regenerating those global contexts, those where clauses, to save a lot of processing time and processing resources. The last component here was added in 11G. This component is actually an extension, kind of your buffer cache for the default database block size. Because your buffer caches depend on the block size. For each database block size that you would use, you have to have a particular buffer cache. Now, your default buffer has a QRC or a query result cache. Now, query result cache is a location where you can cache, as it says, the result of a query. Okay? So if a particular query is reused continuously, then I can put the result of that query into that memory, and then any user that use a portion of that data or that whole query can then use this result set. The difference between this result set and the default buffer cache is the query result cache can be managed based on permanent data keeping. Because to phase out out of the query result cache. There is a parameter. You can decide how it's managed. One of those options are a manual. That means I can put data in there, keep it in there for as long as I want, and then remove it when I don't need it. All right? Very good. That completes the shared pool. Now, large pool. By the way, many of the pools, like the shared pool, large pool, also do many other processes too. Here we're just putting in some of the most important aspects, okay? So we said that large pool is used to hold the UGA for the shared server environment. Large pool is also used by our recovery manager, RMAN. Okay? It is also used for parallel session management. Okay? And it is used when you use the Oracle Automatic Storage Management ASM. The large pool of your database instance and the large pool of the ASM instance, because ASM just uses a database instance. They communicate behind the scene through large pool and synchronize that way. The next component here in the SGA is a small buffer we use that is called the Java pool. Okay, now what is a Java pool? Java pool is used for the Java virtual machine. Oracle database understands Java, and you can create Java objects and use these Java objects for better application management. Therefore, we need to have JVMs to be able to use Java. And finally, the last component here was added in 10G. It is called stream pool. This is for replication. As you all know, one of the original methods of sending data across a network very fast was streaming. Since for replication, you may have to get data across the network very fast, we use the stream pool so you can use streams for data shipping. Now, our SGA is complete. The next thing we need to complete are the background processes. Now, the next background process is one of the very important background processes. It is responsible, one of its major responsibility is instance recovery. Okay? And the name of that background process is SMON, or System Monitor. It is responsible to make sure your database system, meaning your instance and everything, is operating correctly. And during startup, it will perform the recovery for the instance. Of course, with the detailed database operation management, we will cover all of the steps in how the instance starts up and how the recovery taken place. That is for another session. In this session, we basically want to finish up the components. Now, we have another background process that is called MMON. MMON is our manageability monitor. There are some references to it being maintenance monitor. And what is manageability? What is maintenance? Basically, is managing all of the statistical analysis. When the optimizer needs to know how much CPU database is available, how much buffer is available for loading the end user's data, for executing SQL, okay? So all of the system level statistical analysis has to be collected. We normally use a job that is called snapshots and collect those statistics. MMON is a background process that collects those statistics and make sure that the utilities who use this statistical analysis will then get access to them, and then the data is properly loaded into the tables where we store historic and the current statistical information. The last background process we're going to review for this basic architecture review, actually not the last one, the one before the last one, is called the archiver. Okay, the archiver is a background process that allows us to copy the redo log files. Remember, the redo log files are the record of changes. So last night I took a backup at 2 a.m. Database operated from 2 a.m. until 9 a.m. At 9 a.m. my whole server crashed. So now I rebuild the whole database, and now I got to put my data back in. When I restore the backup from last night, I get the data as of 2 o'clock past midnight last night, or 2 o'clock a.m. What am I going to do for the data that was changed between 2 o'clock until the point of crash? Those changes can only be recreated if I have a record of those changes, which is the redo. Therefore, we can periodically copy the redo into an external set of files that are called the archive files. Okay? So these archives are exact file copy of the redo under an archival name and in the archival location you define. We use the archives, as I mentioned to you, to recover to the point of crash. I can use it to recover to a point of time. The user can tell me, hey, I did by accident drop the table yesterday at 8 a.m. So I can use my backup, create a duplicate database, recover it to 8 a.m., pull out the table user dropped, and now I got that table recovered and can put it back in the database. Archives allow me to have standby, because standby has to keep up with the changes, and we use archives to do that. It allows me to do hot backup. I don't have to put database down to take a backup. Users can make a change while we're making a backup, and we can use the change out of archive to move the changes out, forward, or backward to make the backup consistent. We also use archiving if we want to do incremental backup, because incremental backup is also about managing changes. Okay? So archiver allows us to create a copy of the redo into the archive. And of course, when you have so many processes working behind the scene, many times we need to keep track of what they do. Okay? And we need to make sure that they do fire in the proper order. Like at the time snapshot needed, M1 starts up and fires the snapshot. When log writer gets a commit, log writer gets signaled to write the redo. When log writer is done after the commit process, on the next write, DB writer may get the signal to write the change blocks into the disk. Archiver may get the signal that a redo log file was switched, copy the file into the archives. So all of those are managed by another background process. I'm going to put this guy down here, and this guy is called checkpoint. Checkpoint, as I mentioned, is responsible for managing all of these database operations and make sure all of these database operations are properly maintained behind the scene. Of course, if checkpoint is performing all of these checks and balances, it has to write those checks and balances someplace so we can keep a record of it. For example, if my database crashes, how do we know what was the last redo that was written? At what point in time was it written? How much data is in that redo? Where do we go to start? Where do we go to stop? When did the DB writer write the last change? All of that information is located into a data file that we call the control file. The control file has, of course, the structure of my database, meaning which data file belongs to what table space. Where are the control files? Where are the redo log files? Where are the data files located? And where are database operation? When was the log writer write? Okay? So it also holds all of the database operations. So a list of all database operations that took place is also located in the control file. And we have our recovery manager repository. Our man, our recovery manager, keeps a repository of all the backup in the control file. Therefore, that repository can be compared to the database structure. We can see what was backed up, when it was taken place. So our man can perform a lot of very important backup operation for us without us having to keep track of all of that information. So, control file, as you understand, is extremely important. This is basically where all of the metadata about database is stored. Not metadata about your data, not metadata about the table, the metadata about the physical database itself. Without control file, I don't have a database. I don't know where the redos are. I don't know where the data files are. I don't know who has written, whose turn it is, what to do with any of those. Okay? That's why control files are also multiplexed. So we call them control files. By the same set of rules, we talked about the redo log files. We normally might keep 3 of these control files. If you have external redundancy, then you may keep 2 copies. If you don't have external redundancy, you want to keep 3 copies. And these 3 copies are maintained as identical copies for protection. Then, over here, we talked about the parameter file, where it's got all of the parameters that we need to run our instance. Parameter file is about this instance. Okay? What are the information about that instance? And all of the specifications that I need to get that instance started. The last file that we have here on the picture that we're going to talk about that will be done by then with the architecture would be what we call the wallet. The wallet is a server file. In that server file, again, it's not part of the database. It's normally outside the database. You specify where the wallet located in your SQLnet.aura file. Okay? So this way, that SQLnet.aura file can be used to get me access to the wallet. And what do we have in the wallet? In the wallet, we have our certificates. Maybe about our database to identify our servers when we do SSL. Maybe about the user. A certificate can hold user information for the user authentication. In that case, I may have a wallet on the client side. So I can use it when the client wants to connect and extract the information from the wallet for the authentication process. We also hold keys here in the wallet. One key is used for our SSL, as we talked about it. Another key is used for the transparent data encryption. TDE, transparent data encryption, is a means to protect data when it's just sitting there, like in data file, like in the memory, like in the redo. Therefore, we use a key that, with that key, we will then store and encrypt all of our database keys in the data dictionary securely. So when you go create a table and you say column salary encrypt, I don't want the DBA to have access to the key to decrypt that column. That column should only be decrypted if the policy allows the user to see the data. Therefore, the database key that is used to encrypt the column is stored in the database data dictionary with the table, because each table may have a different key. So all of these keys that the database uses are stored in the data dictionary. However, I have to decrypt them to use them. So the master key for the database used for the transparent encryption is then in the wallet. So when the users are using the object, we can use the database master key, decrypt the object keys, using the object key, then decrypt the data for the users. So, guess what? Some people look at that and say it looks like a mess. Other people, they say it's a work of art. Anyway, we have now covered the architecture and the basic components of a standalone database server. So you can understand not only what those components are, but how they are exactly used behind the scene. This concludes our session about the standalone database architecture.